to Social Research Insights. The mission of Social Research Insights is to promote open source tools or software for data analysis for academic and corporate research needs. This is in fact one of the parts of my series of presentations on bioinformatics through our language. In my previous video, I explained few research papers written on GC content, and the GC content will help us to understand the genome of any given species. We can understand the stability, maturity, and the level of organization in the process of evolution of any given organism. So in this video, I'm going to explain how to do that through our language, I mean GC content. So there are two things which we need to know, that is GC content and GC ratio. So they are pretty easy. I mean, they are not difficult actually. This is actually the starting point of data analysis for geoinformatics. I mean, I'm explaining, I just started the data analysis for geoinformatics with a concept known as GC content. So till now I explained only how to retrieve the datasets from some certain world-renowned genome banks, and after that I explained the importance of GC content in understanding the genomic information of a given species through some certain research done by the scientists involving in this domain of knowledge. So now in this video, as I said, I'm going to explain the GC content. The GC content simply stands for actually this concept GC content deals with the GC pair. Guanine, G stands for guanine, C stands for cytosine. So there are two base pairs, that is GC pair and AT pair. So the another pair is AT pair. This is adenine and thymine. So actually the GC content is regarded as one of the important pair that which will help us to understand the genome of any given species or maybe the organism. In short, I can say DNA. So we can understand DNA with the help of GC content, and to do that we have a specific method to compute the percentage of GC content in any given DNA. So if you would like to understand what is guanine, cytosine, adenine, thymine, you please refer to a few other videos, and you can also throw yourself online and pick some research. These are the four important molecules that are the the components of a DNA or a gene. So now coming to these relationships, I mean the bonds, there are two important bonds that we can observe in a gene, that is GC bond and AD bond. The GC bond will be having 3 hydrogen bonds, and AT bond will be having 2 hydrogen bonds. So perhaps this is the reason why scientists prefer to understand genome with the help of GC pair, because it has 3 hydrogen bonds, and which is which might explain the stability of the DNA. So the more the GC content in any given genome simply mean that the more organism evolved and it has become mature. So that way the scientists try to understand the species or microbe or any organism, and try to develop the methods as in the form of cure. So now this GC content can be calculated with the help of a ratio, that is the total number of G plus C nucleotides or molecules divided by A plus T plus G plus C. So this is in precise the method of calculating the GC content. In case if we are interested in GC ratio or AT content, we also have another method, that is A plus T divided by G plus C. So after calculating these measures and depending on the percentage, and this will give the percentage of a ratio that after multiplied with 100, we can convert that statistic into the percentage, and based on the percentage we can take the decision, or we can withdraw the inference whether that particular DNA or the microbe has matured or not. And this is the other metric that we simply call it as AT ratio or GC ratio, or AT to GC ratio, and which ideally need to be 1, which means there are equal amount of AT bonds to that of GC bonds. If it is more than 1, then which means the AT content is more. If it is less than 1, which means the GC content is more. So that way we'll try to understand the nature of the DNA, and already explained you that the more the GC content, more the more stable the genome of that particular organism. So now in R, what happens, we try to find it. We have pretty clear methods in R. First, what we have to do is that we have to import the data set. First we try to import the data set. I already told you how to download the data set from the genome banks. We have 3 important types of gen banks: NCBC, EMBL, and DDBJ. So NCBC is US repository for genomic information or genomes, and EMBL is UK repository or maintained by UK, and DDBJ is maintained by Japan. So this already explained in my previous video. So we just have to retrieve the data set, the gene sequence. In this case we are going to work with gene sequence, and this gene sequence is the part of the nucleotide information of any given species or microbe. So what happens, we just have to download the genome of a given species, and in that genome there will be gene sequence. So this is what is important part of the genome which we need for the data analysis. So after we download the file, so we get the genome is downloaded in the form of a data file. I already told you that this there are different formats of downloading this data file. One of the important formats is FASTA. There are more than half a dozen formats available to download this data file. So one of it is FASTA, is a simple old format which has been used by the scientific community for decades, and the same format is also available from these genome banks. So after downloading this file, usually you'll get it as a sequence dot FASTA. So this is how the name of the file appears, and you can also change the name later in case if you want to make it simple. You can say, for example, if you download the dengue file, the genome of the dengue virus, so you can simply change the name as den FASTA. So there's nothing wrong. So you can open this file with the help of a normal text editor in Windows, or any, for that matter, any operating system like Linux and Mac OS or BSD. Any normal text file can open this file, But in R we have a very simple method to import the data file. That is, we have a simple command. We have a package called sec in R. So that is the name of the package. The package name is sec, all small letters, don't worry about sec in R. So this is the name of the package. So we just have to install this package with the help of a command called install dot packages. So there is a wonderful function to install the packages, sec in R without spaces. So at console and enter. So it will. I did all these as activities, so I need not worry how to install. I'm just telling for your information. In case if you don't have this package, you just have to. And I already told you that there are approximately 6,000 packages available for all quantitative techniques. Numerical analysis through R. So that is the advantage of using R. So the researcher or the data analyst will be having an advantage of installing or picking up any package of his or her needs from this 6,000 packages. So that is the I don't think there is any software suite in this world which can cater such a huge amount of needs. So you name a quantitative aspect, you can immediately find a package in our community, our repository. So you just have to install the package with the help of this function, install packages, open the bracket or parenthesis, within quotes sec sequinr. So after installing the package, so we have a wonderful command known as read faster. So we just have to use read faster. So you just have to spot of the file, path of the file. You just have to put the path within the quotes. Say for example, if you have your file in the F drive, here be careful, this is /, not the backward slash, this is forward slash. F drive or data data. So you just have to put this for example, if the name of the file is den, as I told you earlier, fasta, you have to mention the fasta, just to mention the entire path within the quotes. So you got to be a bit careful while putting the, you just have to. But I have a wonderful way of importing the data file. You need not worry about the entire path. You just have to go to the cursor there, write the read faster, and there is a wonderful function to pick up the file from any drive. File choose, open the bracket, close the bracket, close the bracket. So this is the parenthesis, and this is another parenthesis within the parenthesis, and there is dot inside. So read dot faster, open the bracket, file choose, open the bracket, close the bracket, close the bracket, so that it will try to open a pop-up window. A window will pop up and searching for a file. You just have to go to the browse to the place where you have saved your file, faster file. In this case we have den faster or sequence faster. So when you download the file, it is just sequence faster, but after that, if you change the name, then the faster file, name of the faster file will be the den faster. You just have to spot out that file in your drive, or maybe in the folder, and there will be file inside R. So I tell you a very nice way of importing the file. You better save that entire data that which we import through this function read faster into an object called den left arrow. I explained all these operations in my other videos, when I explained how to deal with data analysis through our language. So you just have to go through those videos in order to understand what I'm explaining in this video cast. So den is actually an object I am trying to create, and I'm going to import the data which is there in this file den fasta in my computer. So now I try to read the data, read fasta file choose. So close the parenthesis, read fasta file choose. There is a bracket here, parenthesis. So now whatever you have done through this statement, that will be preserved in this object called den, and you can verify that later with the help of another command called edit den. So this will let you know what is there in your object den. And later for GC content, so this is the way we import the data to the R editor or to the R console. Now the data is available in the form of a name called den. We have merely created an object, and we have saved all the data which we have downloaded from the repository, the genome bank, and that object is available for data analysis. And now we can simply go for the data analysis. In this case, the data analysis is the GC content, as I have explained you previously. In sequin.r package, this is a package I already told you before. It's a wonderful package to deal with bioinformatics through our language. We have a wonderful function called GC. GC, in this case, we will be doing this action at the console. GC, in this case, the data object is den. But in den we have a sequence, gene sequence, in the first level, as in very first element. So actually, when we created this object den by importing the data through read fasta, it is actually a list object. So if you can verify that with the help of another function called class. So if you verify class den, so it will let you know that the object which you are trying to use for your data analysis is a list object, and this is the way of accessing the list object in R. So a list is actually the list of elements, and there will be levels for a list, and in case if den this list object has any levels, then we just have to go for, we can inquire them as names den. So it will let you know the number of elements that it has at number 1, element number 1, element number 2, element number 3, something. If it has 3 elements, and there will be 3, this is the way to browse the elements den. This particular statement will let you know the very first element of that particular list object, and this will let you know the second element of the list object. In this case, the list is den, the object den 3 double brackets. So this is the third element of the list object called den. So here what I'm trying to do, I'm trying to compute the very first element of the list object, which is known as den, which we had created a couple of minutes ago, and I'm using a function called GC, and this function will calculate the ratio of GC content in the gene sequence which is preserved in the very first element of the list object called den. The den means the object name of the dengue. So this 1 is the element number 1, which is essentially a gene sequence. So when you open the den in editor, then there will be different elements in that object, because this is a list object. In element 1 there will be gene sequence, and this gene sequence is what we are using, what exactly we need in order to, the gene sequence is what we need in order to compute the GC content. So this is actually the total set of actions that we got to perform in our language in order to compute the GC content. So once we get the value, later we'll take the decision. We will try to understand the genome of that particular virus. In this case, the virus name is dengue. Okay, now let's go back to our language. So here the library seqinor. As I told you already, install this package seqinor, which means sequence in R. So we are doing data analysis on gene sequence. So sec stands for sequence in R. So gene sequence analysis in R. That is the meaning of this name of the package seqinor. So use the library statements. You see my other video to know the importance of this function library, and this is the way we put the statement in order to attach the library or invoke the library known as seqinor. So control enter. So I got the library. R is silent, which means it has done some work. If R did not do work, then it will try to return the error here. So there is no error. R is silent, which means it has performed some activity by my when I trigger the action. So now this is the statement which we need to use in order to preserve the data which we had downloaded from the repository. I already downloaded the FASTA file of dengue virus from NCBI. I preserved it in my computer. So I am going to import the data with the help of a function called read FASTA and other function within the function file choose, in order to choose the file from my local directory, and I preserve the data in an object called dengue. So in this case, as I said, den. I'll just simply put it as den. Just a control enter. So now R is as I told you, it pops up a window, and now this is my file which is saved in a folder called data. Okay, so I have this sequence file which I downloaded from NCBI. This is a dengue virus file, and now R is silent, which means it has performed the action, and now I have the object. So let me see if I have this object or not. Class den. Sorry, control enter. Yes, this is list. I told you that this is actually, we created an object which is of the nature list, and this list will be having so let's see what is there in this list. Den. So I told you that the gene sequence is preserved as in the form of the element number 1 in this object den, list object den, and that we are reading into another object called as D sequence. Okay, so let me see what's going to happen. In case if you want to see what is there in your object den, you can simply use edit den, so that you just enter, so that the file will be opened for your verification. You can see the entire file. You see now here what you are seeing is actually the gene sequence in the very first element, element number 1 at the level 1 in list object den. Okay, and now let's take that the very first the gene sequence which is preserved in the very first level in the list object known as den, into the another object called D sequence. So this is the way now R is silent, which means it performed the action successfully, otherwise you will get the error. Now let me see what is there in this object D sequence. It should be having the gene sequence. You see AGTT, GTT, AGT, something like that, all nucleotides. You can see this is actually the gene sequence of the dengue virus. Okay, and now let us go for our final step. We are going to compute GC content with the help of a function called GC, which is available from this package seqinor. Now we use this gene sequence data in order to compute the GC content. So put this sequence within the parenthesis of the function GC and press Ctrl enter. So now you got the GC content. So if you multiply it with 100, then you'll get it in terms of percentage. So there is 46.669, approximately 47% of the content in gene sequence in this. This is the gene sequence. So approximately 47% of the content is GC content. which means it is not even 50% of the entire DNA. So I don't think the dengue virus 1 has nicely evolved, and it is still evolving. As I told you in my other video that there are 5 stereotypes of dengue virus. This is dengue virus 1. So in dengue virus 1 we have only 46% of GC content. In case if you would like to know the AAT to GC content, we have a different formula, and for even the GC ratio we have a different formula that I explained you in my earlier presentation. For GC content we have, when we use GC dense sequence, it is actually trying to compute the GC content with the help of a formula that is G plus C divided by the total content. The total content means we have A plus T plus G plus C. And now in case if we are interested in GC ratio or AT to GC ratio, there is another formula that is AT plus A plus T by G plus C. So this we have to do manually because we don't have any function in Sekinor. So that I will explain you in my next video. Thank you.